Present now. Yes, I want to share that. Yes. There we go. Okay. What's that? Ancient technology. Pencils? I know, right? Okay. So really, we're going to conduct this very similar to how I've been doing the videos, okay? When it comes time to do work, I'm going to do them on my whiteboard up here. But before we get started on anything, I just figured that I'd tell you a funny story that happened to me yesterday. Actually, you'll probably think it's more funny than I did. In my preparation to have students back. So I hadn't changed that board back there with the schedule since November, okay? And after you've left some dry erase marker on the boards, they tend to really want to stay on there. So I have the magical spray that helps clean boards. Oh, geez, helps clean boards. So I rarely use it, but I'm spraying. It's working great. My wife calls me. She's on her way with one of my daughters for an eye appointment. So I'm sitting there chatting on speakerphone and I'm spraying. Well, I came up here to clean this board. Wasn't really paying attention, which is the first mistake. And I went to spray the board, but in the process of trying to spray the board, my finger rotated the nozzle to where it was facing directly in my face. I sprayed myself at point blank range like this. Thankfully, I had my glasses on. And thankfully, it only burns the skin for a few seconds. But my wife and daughter got one heck of a kick out of my misery. And I figured that you would enjoy that because, yes, your misery might be having to come back to school. I'm spraying my face with chemicals. So we're even. Anyway, let's get started, shall we? We're looking at elastic and inelastic collisions, okay? And so you need to have this projected. Anyway, you can follow along in your notes as we go through here. But our objectives in this section are we're going to identify different types of collisions. There are elastic and inelastic, okay? There are ones that as they collide, they stick together. And there are also those that do not stick together. When they collide, they bounce off each other pretty much. We're going to determine the change in kinetic energy during perfectly inelastic collisions. And that's really what our focus is going to be on is the inelastic, okay? In years past, I've done elastic very briefly, and I just usually stick with the inelastic, okay? And then call it the quits on when we get to that last part of the inelastic. We're going to compare conservation of momentum and conservation of kinetic energy in perfectly inelastic and elastic collisions. So that one right there. In tomorrow's discussion, we are going to be looking at not only calculating the momentum of perfectly inelastic collisions, but also the change in kinetic energy associated with that. Okay, so we're just combining things that we've already done. Then we're going to find the final velocity of an object in perfectly inelastic and elastic collisions. Really only inelastic. So let's start off with what a perfectly inelastic collision is. This happens when two objects stick together after colliding and move together as one mass. Okay? Like magnets when they come together. So the conservation of momentum for a perfectly inelastic collision is listed by looking at this formula. Again, total initial momentum, M1V1I, get those confused all the time, plus M2V2I, the momentum of both of the objects in this scenario, is equal to the total final momentum. But since, again, this is an inelastic collision, the objects are sticking together, we sum up those two masses and multiply it by the final velocity. But make sure that is on your formula sheet. Okay? And anytime there is a formula, make sure it gets on your formula sheet. And right off the bat, we get into a practice question. So a 1,000 850 kilogram luxury sedan stopped at a traffic light is struck from the rear by a compact car with a mass of 975 kilograms. The two cars become entangled as a result of the collision, and if the compact car was moving at a velocity of 22.0 meters per second to the north before the collision, what is the velocity of the entangled mass after the collision? Okay, so let's take a look so we can calculate this entangled mass, this scenario that's going on here. All right, so again, let's list what we know. We know that the luxury car, which we're just going to call M1, has a mass of 1,850 kilograms. We know that the mass of the compact car, 975 kilograms. Can anybody tell me what the initial velocity of the luxury sedan was? 0. It said it was stopped at a stoplight. And the initial velocity of the second car, we are told, was 22.0 meters per second north. All right, so that's really all the information we need. And so we go ahead, again, our formula M1 V1I plus M2 V2I is equal to the sum of M1 plus M2 times V final. Where was I? Yes, final. Okay, and that is an F. There we go. And so what we're trying to figure out is what? What are we trying to figure out? Exactly. We're trying to figure out what the final velocity is of the two cars together. So VF. So rearranging to solve for VF, we're going to get M1 V1I plus M2 V2I divided by M1 plus M2. Again, by this point, you might already have some shortcuts, if you will, to these, but I always put in everything that goes along here. So again, just now we have this set up, you can go ahead and plug in your values. So 1850 kilograms times 0 meters per second plus 975. Oh, I messed up here. I didn't get myself enough room. Oh, yeah, I did. I'm silly. Okay. So after you've put those values, that is a 9, by the way. After you put your values in, what is the final velocity of the entangled mess? 7.59. What's the unit? Bingo. Meters per second north. And speaking of direction, I have been, I think I finished. Yeah, I think I finished all the quizzes. Overall, quizzes are really good. Okay. If you miss a point or two, most likely it was because of a directional issue. Okay. So once I still have 1 or 2 people that need to take it. Once I get that, I'll release it to you. You can see. All right. So good. Next, what I want to do is I want you to open up your books to page 213. Yeah. Usually, yes. Yes. Because force typically is associated with acceleration. And acceleration is typically a vector quantity. Okay, what did I say? 213. 213. 213. There we go. Sample problem E. Oh, just kidding. Just 214. Ha ha ha. 214. Let's take a look here. What question should we do here? Tell you what, most of these are just like the one we did, except for 5A. Let's look at 5A, shall we? 5 says a 47.4 kilogram student runs down the sidewalk and jumps with a horizontal speed of 4.20 meters per second onto a stationary skateboard. The student and skateboard move down the sidewalk with a speed of 3.95 meters per second. Find the following. We need to figure out the mass of the skateboard. Okay. So first, let's write what we know. We know that the mass of the student is 47.4 kilograms. We know that student, and we're going to make the assumption that student is running in a positive vector. The velocity is 4.20 meters per second. Excuse me. The skateboard's initial velocity was 0 meters per second. We're going, because it's a stationary skateboard. Okay. Another bit of information we know is that after the student jumps onto the skateboard, they both have a velocity of 3.95 meters per second. Okay. We need to figure out what the mass of that skateboard is. Okay. So let me go ahead and let's rearrange our equation to solve for M2. So after you rearrange the initial equation to solve for M2, what you're going to have is the following. MIVF. So you have M2 is equal to M1VF minus M1V1I all over M1. Why do I keep rust? Okay. So you now have your equation that's going to be set up to solve for your mass of your skateboard. And then we just go ahead and plug everything in. Okay. 47.4 kilograms times final velocity 3.95 meters per second minus, excuse me, 47.4 kilograms times initial velocity of 4.20 meters per second divided by 40, no, where are I? Oh, kids. Who's ready for a really funny joke? Raise your hand if you're really ready for a funny joke. I looked up the wrong problem. Funny joke, isn't it? I did. Me. Mr. Norfler. Not the denominator, though. Yeah, I put the wrong formula in. So you can be mad at me outside of the classroom. Just don't be mad at me now. Okay, kids. We're going to write this correctly now. I'm actually going to put my finger. I had the numerator right. I just looked at the wrong one for the denominator. So I guess you don't have to change that much. I'm telling you, it's all different. Okay. There we go. Perfect. That looks mucho better. So again, just change the denominator. Everything else was okay. So now we go ahead and put our values in. I'm going to put my finger up here again. 47.4 kilograms times our final velocity of 3.95 meters per second minus 47.4 kilograms times 4.20 meters per second. And then we have 0 minus 3.95 meters per second. Okay. It's nothing frustrating than doing that. So what is the mass of the skateboard? 3.0 kilograms. Yes, for those of you at home, I apologize. Okay. Anyway, so that's the mass of the second object. Questions on how to use this and to solve for what you don't know? It's all algebra right now. All right. What I want you to do is jot these numbers down. Okay. These will be your homework for problem bank E. 1, 2, 5, 8, 9. Again, these are numbers that you will do. 1, 2, 5, 8, 9. Okay? So I will be posting problem bank E in the next few moments. Those of you who are watching at home, feel free to leave as you so please. I'm going to be stopping the recording. Okay, if I can figure out how. There we go. So stop recording.